Section: Introduction. We're exploring how to train smaller, specialized language models efficiently, especially when there's not a lot of specific data available for the task at hand. Our goal is to achieve good performance without the high costs associated with running large models, which can be prohibitive, especially on mobile devices. To do this, we focus on three main strategies: using a broad set of training data, selecting data samples that are most relevant, a technique known as importance sampling, and designing models that are smaller during actual use than they are during training. This can involve methods like mixtures of experts or hypernetworks, which essentially means using a combination of smaller models or adjusting the model based on the task. When considering the costs of training and running these models, we look at four key factors: the initial cost of training on a wide range of data before focusing on the specific task, the cost of then training the model on this specific task data, the computational cost of using the model to make predictions, and the amount of specific task data we have to work with. We're particularly interested in how to balance these costs to make the most efficient use of our resources. We compare different approaches to see which ones offer the best trade-offs between performance and cost at various stages of the training and deployment process. Here's a brief overview of the methods we consider. 1. Large model approach. First, we train a large model on a broad set of data and then use it as is. This requires a lot of resources up front and doesn't adapt to specific tasks unless we further fine-tune it, which adds to the cost. However, it's a straightforward approach when resources aren't a concern. 2. Parameter-efficient tuning. Here, we fine-tune just a part of the model on the specific task data. This is useful when that data is limited, as it helps prevent the model from overfitting. It's a more resource-efficient way to adapt a model to a new task. 3. Small model approach. We train a small model from the start, without using a large dataset first. This keeps both training and running costs low but might not perform as well without the broad knowledge a large dataset provides. Fine-tuning can help improve its performance on specific tasks. 4. No pre-training. This method skips the broad training phase entirely and trains a small model directly on the task-specific data. It's useful when there's plenty of such data or when the task is very different from anything in the broad training set. 5. Importance sampling. Before training on the specific task, we select a subset of the broad training data that's most relevant to the task. This can help improve performance when task-specific data is scarce. 6. Distillation. We use a large, fine-tuned model to teach a smaller model. This can help the smaller model perform better than it would on its own, as it learns from the larger model's broader understanding. Each of these methods has its pros and cons, depending on the amount of data available for the specific task, the resources available for training and running the models, and the performance requirements of the task. Our study aims to guide the choice of method based on these factors. Section Summary. The section discusses the challenges of using large language models due to their high inference cost, especially on mobile hardware, and proposes training small specialized models with limited domain data. The paper explores three key elements for achieving low perplexity in small specialized models: generic training corpora, importance sampling, and asymmetric models with fewer parameters at inference. It also compares different training approaches based on generic training cost, specialization training cost, inference cost, and size of the specialization training set, while considering operating curves resulting from varying the generic and specialization training costs. The paper presents different strategies for training large language models, LLM, parameter-efficient tuning, small language models, SLM, and methods like no pre-training, SLM-NOPT, importance sampling, SLM-IS, and distillation, SLMD, to address the challenges of specialization data and inference constraints, providing insights into their advantages and limitations. Section: Hard Mixture of Experts, SLM Mix. We explore a method called Hard Mixture of Experts, or SLM Mix for short. This approach involves breaking down a large dataset used for pre-training into smaller groups, for example, by clustering. Then, we train a smaller model, which we refer to as an expert, on each of these groups. The cost of pre-training and the total number of parameters increase with the number of groups we create. When it comes to using these models, we typically send each data example to the expert that was trained on the group it fits into. Once we have specific data for a particular task, we choose one expert for that task. We might pick the expert trained on the group that shows up most in our task-specific data, or if we have enough resources, we choose the expert that performs best on this data. Choosing one expert per task is efficient because it means we only need to use a small part of the model's information for that task. However, this approach might not work as well if our task-specific data doesn't neatly fit into one group. SLM mix models can be further refined. If we have a lot of resources, we can improve each expert and then pick the one that does the best. With fewer resources, we might only refine the top-performing expert from the pre-training phase or the one trained on the most common group in our task-specific data. This second approach costs about the same as just refining the SLM model. Next, we discuss hypernetworks, or SLMHN. Hypernetworks consist of two parts. One part generates weights for the other, which we call the instantiated subnetwork. We use hypernetworks to create a mixture of experts by having the first part generate weights based on which group an input belongs to. This method allows us to share parameters across experts and choose how big the overall model and the number of groups should be independently. We can also refine these instantiated subnetworks with task-specific data. For our experiments, we use a dataset called C4, which is a large collection of English text. We prepare this data using a tool that breaks the text into pieces and have a vocabulary of 32,000 words. We focus on adapting our models to 9 different areas, ranging from science articles to legal texts and forum discussions. We vary the amount of data we have for each area. To group our data, we use a method that turns documents into numerical vectors and then groups them. We experiment with different numbers of groups. Our experiments are conducted with transformer models of two sizes, a smaller one with 126 million parameters and a larger one with 770 million parameters. We train and test these models with pieces of text up to 1024 words long. In distillation, we use a larger, refined model as a teacher to improve a smaller model trained on general data. This process focuses on making the smaller model's predictions closer to those of the teacher model. The main costs here are training the teacher model and refining it with task-specific data, with an additional smaller cost for training the smaller model on general data and then refining it with task-specific data. Lastly, we train hard mixtures of transformer models for pre-training. We group the pre-training set and train an independent small model on each group. For refining these models with task-specific data, we use a straightforward approach of identifying the most common group in the task-specific data and refining only the model trained on that group. This method is particularly useful because it allows us to work with a large model while only needing to refine and run a smaller model for specific tasks. If resources are limited, we can skip training models on all groups and instead focus our resources on refining a model for the most relevant group once we have the task-specific data. Section summary. The hard mixture of experts, SLM mix, method involves dividing a large pre-training set into smaller subsets and pre-training a small model on each part, with the pre-training cost and overall number of parameters scaling linearly with the number of clusters. Inference with a hard mixture involves forwarding each example to the expert corresponding to the cluster the example belongs to, and the method can be fine-tuned with a large specialization budget to select the best performing expert. On the other hand, hypernetworks, SLMHN, uses neural networks to create a mixture of experts, sharing parameters across experts via the hyper-subnetwork and providing a flexible way to independently select the capacity of the mixture and the number of clusters, with the instantiated subnetwork being fine-tuned on specialization data. Section: Hypernetworks. We discuss the concept of hypernetworks, which are essentially neural networks where the weights are determined by another network, known as the hypernetwork. This setup is based on specific input variables. In our scenario, we link each example to a cluster membership variable, as outlined in the clustering section. This variable serves as the input for the hypernetwork, which then generates the weights for the layers of a transformer language model, excluding the first two layers. The rest of the transformer's parameters remain unchanged across all examples. Our hypernetwork creates two sets of weights for each layer and cluster. It operates based on two key settings: the size of the latent dimension and the number of experts. Each cluster is represented by an embedding in the latent space, and each layer is linked to a matrix. The weights are calculated as the weighted sum of a vector and two three-dimensional tensors, which vary in shape. These tensors contain a significant portion of the model's parameters, allowing the model to increase its capacity by raising the number of experts without enlarging the model size for each cluster. While we present one possible architecture for hypernetworks, there are many other designs that could be explored. Hypernetworks have certain limitations compared to hard mixtures of experts, particularly in terms of capacity, as the training cannot be divided into smaller, independent tasks. However, they offer the advantage of training the weights of all experts together, making the model more efficient in terms of parameters. For specialization, we adopt a strategy similar to that used in hard mixtures. We select the model based on the most common cluster in the specialization set and then fine-tune it. This fine-tuning process only involves the smaller, instantiated model, not the larger hypernetwork. We also introduce an important sampling method that utilizes k-means clustering. This method is designed for streaming and only requires the frequency histogram of cluster occurrences in the target distribution. It uses a large buffer of pre-training documents and selects documents from each cluster to match the target distribution histogram, ensuring a balanced training dataset. For evaluation, we use perplexity, a standard metric in language modeling, measured on a set of held-out documents. Our focus is on language modeling performance, not on downstream tasks like question answering or translation. We report the training costs in terms of hours spent on graphic processor units, considering both pre-training and specialization phases. Our empirical results show the performance of our models in terms of parameters, throughput, and training costs. Despite having a larger number of pre-trained parameters, our models achieve better perplexity than a large language model, LLM, when fine-tuned on specific clusters. We also observe that fine-tuning significantly improves perplexity across all methods, highlighting the importance of a good starting point for training. Interestingly, as the size of the domain-specific training set increases, the advantage of starting with a better model diminishes. Our method without pre-training shows the best post-specialization perplexity, especially when in-domain data is limited. Section Summary. The section discusses the concept of hypernetworks, which involves using a secondary network to generate weights for a neural network based on a conditioning input variable. The hypernetwork produces feed-forward matrices for a transformer language model, with the parameters depending on the cluster and the number of experts. Additionally, the section introduces an important sampling method based on k-means clustering and evaluates the models using perplexity as the main metric, along with training costs and empirical results. Section: Small and Large Models. We explore the performance of both small and large models by comparing their perplexity, which is a measure of how well a model predicts a sample, on different subsets of a dataset called the pile. Our findings show that both pre-training and fine-tuning are crucial steps to improve a model's performance on specific areas of interest. Without pre-training, a small model requires a significant amount of data, specifically 64 million tokens per domain, to achieve decent results. However, we notice a substantial improvement in performance for both small and large models after fine-tuning, even with just 1 million tokens from the relevant domain. This highlights the importance of fine-tuning in enhancing model performance. Additionally, our results confirm that large models, when given sufficient resources for inference and pre-training, benefit from being trained on a large dataset known as C4. In our distillation process, we use a large, pre-trained model, teacher, and a small, pre-trained model, student. We first fine-tune the teacher model on a specific dataset and then use this fine-tuned model to guide the training of the student model on the same dataset. This process involves balancing the costs of pre-training both the teacher and the student models. Our experiments show that when the teacher model is pre-trained for a sufficient amount of time, over 276 GPU hours, the student model performs significantly better than if it were trained alone on the specialized dataset. However, when considering the combined pre-training costs of both teacher and student models, the student model does not outperform other methods that do not involve distillation. Our approach to using a mixture of experts involves dividing a general dataset into clusters and assigning an expert to each cluster. For fine-tuning, we only adjust the expert associated with the cluster that appears most frequently in the domain-specific dataset. We experimented with different numbers of clusters and found that having too many or too few experts can either increase training costs unnecessarily or lead to underfitting, respectively. Our main experiments use 16 experts, and we compare the performance of models with 4 to 256 experts. We also explore different strategies for selecting the best expert for fine-tuning and find that fine-tuning all experts and choosing the best one afterward, although more expensive, yields the best performance. Interestingly, fine-tuning only the expert for the most common cluster in the domain-specific data allows for a more efficient allocation of training resources, as it enables focusing on a single model once the target domain is identified. However, this approach does not perform as well as using importance sampling, a method for selecting training samples based on their relevance. Lastly, we discuss hypernetworks, which allow us to adjust the total number of parameters in our model while keeping the size of the model used for making predictions constant. Our findings indicate that increasing the number of experts improves performance per iteration, but having 32 experts strikes the best balance between performance and computational efficiency in our setup. Section Summary. This section discusses the comparison between small and large transformer models, emphasizing the necessity of both pre-training and fine-tuning for achieving good perplexity on specialization sets. The distillation process involves using a pre-trained teacher to supervise a pre-trained student, with the cost of generic pre-training being distributed between the teacher and student. Additionally, the section explores the hard mixture of experts, varying the number of clusters and discussing the trade-offs between training cost and model capacity. It also delves into hypernetworks, highlighting the impact of the number of experts on the overall number of parameters and the efficiency of compute time. Section: Importance Sampling. We use a technique called importance sampling to adjust the dataset we call C4 so that its groupings of data, or clusters, look similar to those in a specific subset of a larger dataset known as the pile. The number of these clusters is crucial. If we use too few clusters, we'll only be able to make broad, less precise adjustments to the C4 dataset, resulting in a rough approximation of the target subset. On the other hand, using too many clusters can cause two problems. First, if our target subset is small, it's hard to accurately figure out how often each cluster appears when there are many clusters. Second, with many clusters, the target's data might end up being too concentrated in a few small clusters. This would mean our adjusted C4 dataset would have a lot of duplicate data points from these few clusters, which isn't ideal because it effectively reduces the variety in our dataset. In our main findings, we talk about using 1024 clusters. We also show what happens when we use 16, 64, 256, and 1024 clusters. It's important to note that we don't start using the importance sampling method until after we've decided on the specific subset we're targeting and have a model pre-trained on a different dataset for each specific task. This approach means that importance sampling requires more effort for each new task compared to simply fine-tuning a model, and this difference becomes more significant as we tackle more tasks. When we look at the overall effort needed to adapt a model for multiple tasks, we find that for some methods, like using hypernetworks, most of the effort comes from the initial, general pre-training. The main way to change how much effort is needed overall is by adjusting the amount of this pre-training. For importance sampling, there's no initial pre-training effort, and the main factor that affects the total effort is how much training is done on the specially selected pre-training dataset, which is part of the adaptation effort. We explored how the effort changes for two of our methods, SLMHN and SLM-IS, as we increase the number of tasks from 1 to 7 to 50. we found that importance sampling becomes less appealing as the number of tasks grows. The effort needed to fine-tune the SLMHN model, which grows linearly with the number of tasks, is relatively minor, taking about 1 GPU minute per task. Moving on to related work, adapting language models to specific domains has been around for a long time, even before models based on neural networks were popular. This line of research started from noticing that models trained on a lot of data, even if it wasn't closely related to the target domain, could still be very useful. With the introduction of neural network-based language models, there was a push to train these models on ever larger datasets to improve their performance. However, this approach has to balance between using a large, general dataset to minimize errors and using a dataset that closely matches the target application to ensure the model performs well when actually used. Techniques like fine-tuning the model and learning multiple tasks at once have become key strategies to get the best of both worlds, benefiting from large, general datasets while also focusing on the specific needs of the target domain. There have also been efforts to pick and choose data from the general dataset that would be most relevant for the target application, a process that ties back to the concept of importance sampling. Alongside the growth of language models, there's been concern over the cost of using these models, leading to research on making model use more efficient through methods like making the models smaller, simplifying the models, or cutting out parts of the models. Another approach to keep models efficient without sacrificing their capabilities too much involves using a mix of specialized components within the models.